So let's start, everybody. Welcome again to the Neuro-Symbolic AI virtual talks organized as part of the Alan Turing Institute. It's our pleasure to have Eleonora today. If you're familiar with Eleonora's work, she's been quite prominent in publicizing the ROAD-R dataset, which was highly influential for understanding how constraints might be used for self-driving and automotive understanding. Previously, Eleonora completed her PhD at the University of Oxford with Thomas Lukasiewicz, and then she was at Vienna for 1 or 2 years. And is it 2 years, Eleonora? 1 year,
Yeah, 1 year
okay.
and a half.
1.5. And now she's starting as a new faculty member at Imperial. So Eleonora, take it away.
Yeah, thank you very much, Vaishak, for your very nice introduction. And yeah, thank you very much for having me here. It's obviously a pleasure for me to be talking at the Alan Turing Institute, since we are all in London, and it's nice to be able to share our ideas with, fellow people here. So yeah, let's start. What is the topic of the talk today? So as Vaishak said, one of my works was on ROAD-R, which is this dataset for ensuring the compliance of deep learning models with like constraints. But more in general, this dataset was a part of a bigger effort that I've been trying to push for the past 6 years, which is how to create deep learning models that are compliant with requirements, and in particular to push this view that the requirements actually have a key role to play into the realm of deep learning. So let's see why do I think this, and what is in general the problem that now many years ago I wanted to solve. So the problem that I wanted to solve when I started my PhD now 6 years ago was the fact that deep learning is great. I personally got really into it because it was giving great results in natural language processing, and you can really do things with deep learning that, let's say, 10 years ago were completely unmanageable. However, even though deep learning is great, it can still exhibit some behavior and make mistakes that an intelligent being would never make, right? And some of these mistakes are actually so bad that they make the news. And so we have these big titles on the New York Times saying, oh, AI is very bad because, Tesla is using it and driverless cars are killing people now. So obviously, trying to solve this problem, trying to make these models behave in a bit more intelligent way or less unexpected is obviously a big problem. And obviously, when I started my research, I was like, oh, how can I solve this problem? And then I always say, research kind of humbles you. And so now this is, wait, I think maybe you see this. So yeah, now, as I was saying, the new question is, how can we alleviate this problem? So I am an engineer by training, so I started to study this problem from a holistic perspective. And so I started to see what is the general pipeline of a machine learning model. And so this is the pipeline that I think if anybody of you has ever trained a machine learning model, this is kind of the steps that you follow. So you take a data set, you clean it, you curate it, you do all the steps like data imputation, normalization, whatever. Then once you have your data clean, what do? You create a model, right? Which can be a neural network if you work in deep learning, different models, transformers, convolutional, but it can also be decision tree, whatever. Then once you have your model, you train it, okay, using a loss function that you design. And finally, you test it, hopefully on a data set that is different from the one that you trained. So let's compare this with the standard software engineering pipelines, which are the ones that I studied back in the days, and now I'm starting to teach to students. So if we take a standard software engineering pipeline, we have the waterfall, the agile, and okay, this is spiral, which is a bit more complicated. But I think everybody here can notice a very big difference. And what is this difference? Well, the difference is that if you think about it, all of these pipelines always start from the requirements definition and elicitation. And if you think about it, whenever you, I don't know, attended a course or you're teaching a course on software engineering, you always tell the students, don't even think about writing your code if you don't know what are the requirements of your problem. So the obvious question is, how come this sort of approach is not used also in deep learning, right? In deep learning, as you can see from the pipeline, we don't have any requirements, elicitation or definition at any point. And then essentially people, what they've been traditionally doing is they take some data set, they train the model and they see what happens. But this is fine if, these models are used in sort of a standard way, which is a more statistical one, where you have, predictions, a model that is just a statistical model that makes predictions. However, now it's becoming really important to have this step. Why? Because these deep learning models are actually becoming part of our daily lives. They are taking decisions that have consequences, that can actually, have consequences in the real world. So I think this should be a major shift in how we treat these models. We should stop treating them as statistical models, but actually as algorithms, as whatever, systems that act in the real world and needs to have the same safety guarantees as all the systems that act in the real world, be it software, be it transportation means, things like this, right? So we need to have requirements. So obviously, when I started this, I wasn't the only one that was thinking about this. There were actually some very cool works that were doing either verification or testing. So just to give you an idea, a verification technique for a deep learning model in particular is a method that essentially creates an abstraction of your neural network, but then you can pass, for example, to an SMT solver, and then this SMT can check, okay, is my neural network now compliant or not with some properties, or does it show some property? And then we have testing techniques, right, which are techniques that essentially try to generate datasets, testing datasets that can sort of cover the entire distribution, possible distributions of your inputs. And in this way, you can find all the shortcomings of your model. So these honestly were personally very inspiring. I mean, these are just two examples, but there are a bunch of methods. One from Marta, for example, Kwiatkowska here at the Alan Turing Institute, which were very, very inspiring. However, personally, I had this problem with methods, which is that, as you can see, they act very late into the pipeline, okay? So I started wondering, okay, can we do something that happens, a bit earlier into it? And so this is how I came up with my great research question, which is, how can we build models that are compliant by design with a set of requirements, okay? And at the same time, learn from the requirements themselves. Why is there this duality? Why this double sort of objective? Well, this is actually very important for my research and in general for me, because, when you listen to the standard narrative for machine learning, normally people say, oh, you have to have a compromise between safety and performance, okay? And this is a personal opinion. I disagree with that. Why? Because requirements encode background knowledge, right? And if you think about it, neural networks don't work like because of magic. We don't use standard feed-forward neural networks. But what we are doing is injecting into this neural network smart inductive biases, which we design from our background knowledge about the problem, and then they work. So for example, convolutional, they work because we know that images are, for example, translation and rotation invariant, right? So it's fine to inject background knowledge. Actually, it's needed, and requirements express background knowledge. And I would like to have a way of transforming requirements in smart inductive biases that we can use to also get better performance, not only make neural networks safer. Okay, so now that we have all the preamble done, and we have seen, okay, what is the general goal? Let's start to see how can we actually do this. And as you will see throughout the talk, I like to do these things with examples. So I like to show the results with examples. So let's start with this very, very simple problem. Suppose you have two classes, A and B, okay? And suppose that you have a requirement that tells you A implies B. How do you read this? Well, this can be read as, whenever you're predicting the class A, then you should also predict the class B, okay? This is a very common type of requirement. For example, think about the GFAR dataset, where you have, for example, in the extended version, you have airplanes, which is also a means of transportation, right? So whenever you have a class airplane, you should also predict the class means of transportation, right? Okay, so we have these two classes with this requirement, and also just for visualization purposes, suppose that your data set is between 0 and 1, so we have a 2D, very simple data set, and that the data points are distributed as in the image. So how do you read the image? So you see that the data point belongs to the class A if it falls inside the tiny rectangle, okay? So blue data points belong to the class and red don't. And for the class B, we have that if the data point belongs to either of the rectangles, then it belongs to the class B, okay? So as you can see, our data set is actually compliant with the background knowledge. Also, for just the sake of notation, this is how I will denote the ground truth. And so, for example, we will say that this data point has ground truth 0, 0 for both A and B. And for this one, on the other hand, we will have that the ground truth is 0 for A, but is 1 for B, okay? Okay, so how would you normally treat this problem in standard deep learning setting? Well, we would take a neural network with 2 inputs, 2 outputs, something in between. Standardly, we will call this neural network a function h. And this neural network will have 2 outputs, h of a and h of b, which essentially will output 2 values between 0 and 1, telling us the confidence of a neural network that the data point belongs to either the class A or to the class B. Given this neural network, what do? Essentially, we train it with a standard binary cross-entropy function. So I include here the equations of the standard binary cross-entropy function, and essentially just sum the 2 of them, and you get the loss function that then you use to train. So actually what we have done to see how this would work in reality, we actually trained a very tiny neural network with just 7 neurons on exactly this task. And with such a tiny neural network, this is the results that we get. So what we can see that obviously with very few neurons, first of all, we can see that the neural network struggles to learn our rectangles. So how do you read these plots? Sorry, obviously first I should tell you this. So the more red a region is, the more confident the neural network is that a data point falling in that area doesn't belong to a class. So you have the mapping at the very far end of the picture. And the more blue a region is, the more confident the neural network is that the data point falling in that area actually belongs to the class, right? So as you can see, the neural network is kind of struggling to learn the right decision boundaries, right? And also, if you look, in particular in this corner, you can see that even if it's such a simple case, with such a simple requirement, the neural network is actually learning something that violates our background knowledge. Why? Because you can see that the output for the class A for that region is actually higher than the output for the class B. So there will exist a threshold for which the class A is predicted and B is not. Okay? So this has shown us that with a tiny, very, very tiny neural network, actually the neural network can struggle to learn these functions, and also it can output something that violates our background knowledge. My question now is, can we do something better? And the answer is yes. So what is our work? What is our intuition? Well, the basic intuition we had is that obviously the requirement essentially defined what we call the safe output space of a model, okay? So if we were to plot what is the output space of a model, we get exactly this square, right? So the neural network can output anything between 0 and 1 for both of the outputs. And if we look at our requirement in the propositional logic case, essentially the requirement propositional logic is telling us, okay, you cannot have the output in this point, which is you cannot have the output equal to 1 for A and 0 for B, okay? Now, this is fine if you're reasoning in the discrete case, but if you think about it, neural networks don't work in the discrete case, they are continuous. So can we in some way also reason in the continuous case? Well, the answer is yes. And if you think about it, actually our requirement in the continuous case is defining all of the red region as the region that violates the constraint. Why? Because if you think about it, whenever the output for the class B is lower than the output for the class A, then there will always exist a threshold for which A is predicted by B is not. So essentially, what we need to do, our new task, is to ensure that our output can only be in the white triangle above, right? As simple as that. And how can we do this? Well, again, the intuition is very, very simple. What you can do is simply add the requirement layer on top that changes the output of your neural network. And what does this layer do? Well, as you can see, I have the equation here in the slide. It leaves the output for the class A unchanged, and it changes the output for the class B to a maximum between A and B. Now, H prime B is always guaranteed to be greater or equal than the output for the class A, right? Is always greater or equal than HA prime. Okay, so this is great. So now we have that the final output is guaranteed to be compliant with the requirement A implies B. And the network is now aware that A is a sufficient condition to conclude B. Why I'm saying this? Because I don't know if you are aware, if you know about the T norms, but essentially what we are doing is rewriting B as A or B using the Gödel T norm, which makes total sense because if you know that A implies B, then writing B or writing A or B is exactly the same thing. However, there is a caveat. If we were to naively add this layer on top during training time, this can give us wrong supervision. So we need to pay attention. What does it mean causing wrong supervisions? I will elaborate on this. So we have our layer and we have our loss function, right? Our loss function is nothing else than the binary cross-entropy function that I showed you before, okay? And it's just taking instead of HA, HB, H prime A and H prime B. Okay, we are good. Now, what is the intuition? Whenever we have the ground truth for A equal to 0, we cannot teach a neural network to rely on the output for A to reach a conclusion for B, right? Because if you have A implies B, if A is 0, you cannot conclude anything on B. And indeed, this is the reason why this gives us the wrong supervisions. Indeed, suppose you have this scenario. The output for the class A is greater than the output for the class B. And we have that the ground truth for A is 0. but the ground truth for B is 1. Now, what would happen? It would happen that the outputs for HA and HB are both equal to H of A. And then our losses would be exactly this, right? If you do the substitutions, you get this loss function. And this is interesting, right? Because essentially, our loss function is teaching the neural network to increase and decrease the output for A at the same time. So obviously, this can cause big problems. Can we fix this? Well, luckily, yes, and it's really just a tiny trick. So this is a new loss function, which is just a very tiny modification of a binary cross-entropy function, and now we will parse it. So for A, we don't change anything. We let it be as it is. Now let's have a look at B. If we look at B, whenever the output for the ground truth for a class B is 1, again, we are back to the standard binary cross-entropy loss. However, when the ground truth for B is 1, what do we have? We need to have that we multiply, instead of just passing H prime of B, we pass H prime of B, but modified a bit, so that H of A is multiplied by H of A, right? By Y of A. So now we have that if we take all of this, we get that the loss is correct. We are teaching that A should decrease and B should increase. So we are good. So with this simple modification of binary cross-entropy loss, we actually managed to use the maximum, okay? So now, I know this was a bit tedious with the math, but it was just to say, you know, actually it's a fun story. Like when I first thought about this maximum thing, I was sure that somebody else would have already thought about this. And then I went to Marco Gori, who is a super famous professor in Italy, and I was like, do you know of anybody doing this? And he was like, no, I don't know anybody, but I think it's because nobody thought of this loss function, right? So I think the real trick here was to understand that maximum has some great properties, but it can have some problems with the gradient, so you need to take care of it. Okay, so now we can go back to our example, and we can show now that if we take exactly the same neural network, okay, with 7 neurons, and we simply add our layer on top, then we get these decision boundaries. And as you can see, not only the constraint is always satisfied, but we also get that the neural network is learning the right thing, right? So it's actually able to learn the function in a better way. Now, the obvious question is, like, how is this possible, right? Because if you think about it, we haven't added any weights. We are only adding a maximum. So how is it possible that the neural network with no more parameters is suddenly being able to learn a function that before it wasn't? Well, to answer this question, we need to have a look at what happens before the requirements layer. So I would like to plot now what happens, what are the decision boundaries for HA and HB, not for H prime and HB prime. So if we plot the decision boundaries for HA and HB, we get this. So this is cool, right? Because what does it show? It shows essentially that the neural network is learning that A is a sufficient condition for B, right? So it doesn't need to output 1 also for the rectangle above on its B output. Why? Because it knows that it's already taken care of by A, right? So then you can use a maximum to compose back the problem, and that's it. So essentially, thanks to our layer, the network now knows that this problem can be decomposed into simpler problems, and it doesn't have to waste its own parameters to learn redundant information, right? It can just use it to learn a better function for B. And yeah, I mean, this is the general idea. Like personally, I've learned that neural networks are incredibly lazy objects. So if they can, they will always take the simpler path. So if we give them a way of learning in an easier way, then they will take it. Okay, so we have seen that if we have the two rectangles, one outside the other, then the neural network, thanks to the layer, can now decompose the problem and get the easier one. Now, an obvious question would be, okay, wait a second, this is nice in this particular scenario, but it's not always the case that it's convenient to decompose B. And I agree. So to show that our layer is not forcing the neural network to decompose, but it's just telling it, okay, if you want, you can decompose. We have actually moved the rectangle inside. And as you can see, the neural network manages again to learn very good decision boundaries. Why is that the case? Well, again, let's have a look at what happens before the requirement layer. And as you can see, now the output before the requirement layer is exactly the same as afterwards. So the neural network in this case is not exploiting the layer, it's just learning B as a whole. And why is that the case? Well, because neural networks are lazy objects, so learning a rectangle, which is a convex function, is much easier than learning a donut, which is what they would be required if we were to decompose the problem. So essentially, the main takeaway point here is that if we add this requirement layer, then essentially we are telling the neural network, if you want, you can decompose this problem, but if you don't want to, then it's fine. Okay, so this was the case for one very simple hierarchical requirement with two classes. What happens if we have multiple requirements? Well, it's very easy to generalize this because if you think about it, for each label A, it just takes the maximum between its own output and the one of all its descendants or all its subclasses in the hierarchy. And for the loss function, again, we are simply changing the binary cross-entropy function to work with the layer, right? But the real thing is adding the layer. So for hierarchies with multiple hierarchical constraints, it's very, very easy to work things out. And believe it or not, even for this very sort of simple application with very simple requirements, you already have a lot of possible applications. So you have a field of functional genomics where you have proteins that need to be mapped to protein functions, which are literally organized in taxonomy. You have fine-grained image classifications, which again, where again you have an image, and then you want to have enable a different level of granularity, and document classification is the same. So, as I said, if even if you are thinking, okay, hierarchical requirements are very easy, true, but they are already very, very much studied. And yeah, so I will close on hierarchical requirements, but before closing it on it, I just want to show this table where CCN plus is our method, which is a simple feed-forward neural network with this requirements layer on top of this modification of binary cross-entropy loss. And why I always show this table? Well, because these are 21 datasets that are very well studied by the community that studies multi-level classification with hierarchical constraints. And all of these, all of the others are state-of-the-art models that were particularly designed for this problem of having multiple classes organized with a hierarchy. And with a smart injection of this background knowledge, we managed to beat all of them in most of the scenarios with a simple feed-forward neural network with 2 layers and this modification on top. So this is just to take a, to really say, yes, requirements make it neural network safer, but can really also help in improving their performance if used smartly. Okay, we have finally finished on hierarchical requirements. Now, can we do something a bit more interesting? Well, obviously, yes. Let's see how. So suppose you have a single requirement of this form, so a rule. This requirement, what is telling us? Well, this requirement is telling us that if you're predicting the classes A1, to AK, but not the classes AK plus 1 to AN, then you should also predict the class A. If you have this requirement, what is actually telling you, given this, the output space I showed before? Well, this requirement is telling you that actually there is a lower bound for the class A, which is defined by this function, which is nothing else than the Gödel-T norm transformation of the body. And why is this the case? Well, if you think about it, if you have this requirement, essentially you need to say, okay, I need the prediction for the class A to be the highest between what? The minimum of my body. So the positive prediction for the classes A1 to AK, and 1 minus the predictions AK plus 1 to AN. Okay, so if we have a rule with a positive head, we are done. We can be happy. What if we have a single requirement of the form A1 and A2 and AK and not AK plus 1 to AN implies not A? Well, this defines an upper bound for the class A, right? And the upper bound is nothing else than 1 minus the minimum between the value of the values of the body, right? So now we know that if we have exactly one constraint with positive head, we have a lower bound. And if we have exactly one constraint with negative head, we have an upper bound. That's it. So if we have one requirement, we are done, okay? Now the question is obviously what happens if we have more? Because if you have more, then we need to take care of interactions between these requirements. Okay, let's see what happens. And suppose we have now proposition logic requirements. And I would like to show this through an example. So for this, suppose you have a neural network with 4 outputs, blue, green, yellow, and red. And suppose that these are your requirements, which are expressed in CNF. How do you read this? Well, a full dot is a positive literal, and the empty dot is a negative literal. So the first one can be read as green or not blue or red. The second one is not blue or not green or yellow. Okay, so suppose we have these requirements in our neural network, and we want to get a layer that essentially has the following properties. It needs to be added on top of any neural network. It needs to allow gradients to backpropagate through it. It needs to have no cycles, right? Because otherwise it makes the backpropagation much more complex, and also it's really time consuming, and you don't want that. So suppose that's our goal. We want to have a layer with these properties that can be added on top of a neural network. How can we do this? Well, first of all, in our approach, we need to define an ordering over our labels. In this case, we take blue, green, yellow, and red. What is this telling us? Well, this is telling us nothing else than green needs to be computed, the value for green needs to be computed on the value of on the ground of the value for blue. The value of yellow needs to be computed on the ground of green and blue, and so on and so forth. So it gives us a computation ordering. Okay, so what can we do with this ordering? Well, the basic idea is that we want to go back to rules, okay, that we know how to deal with. And actually, thanks to the ordering, that's exactly what we can do. So how can we get these rules, though? Because obviously the question is there. Well, in order to get these rules, we need to traverse the ordering in a opposite direction. So we start from red, and what do? We take the 2 clauses where red appears, and we transform them into a rule by simply using the property that not A or B is equivalent to A plus B, right? So if you take the first clause, if you look at it, the body of the first rule is nothing else than the negation of no green and blue implies red, right? So this gives us the 2 rules where red appears in the head. The question is, where does the third rule that I highlighted come from? Well, these rules come from the resolution between the rule where red appears positively and the rule where red appears negatively. Why do we need to do resolution between these two rules? Well, because if you think about it, you cannot activate at the same time the rule that entails red and the one that entails no red. This would lead us to a prediction that makes no sense. We cannot have red and not red at the same time. So we need to make sure that the two rules cannot be activated at the same time, that don't give us contradictory labels. So how do we do this with resolution? And indeed, if you think about it, again, we get that if it is not green and blue, then this deactivates yellow, right? So essentially, it's easy. Okay, so now we have taken care of red. We can move on to yellow. So we move on to yellow. We can forget about the two rules where red appears, and we need to just transform the second clause into a single rule, right? Then what we will need to do? We look for other clauses where yellow appears negatively. There is none, so I don't need to do resolution. Then I move into into green. There are no clauses left considered where green appears, because we have already considered all of them, so I need to do nothing. And the same for blue. I have already considered all my clauses, so I can just move on. Okay, so now essentially we have moved from the realm of clauses that we didn't know how to deal with to the realm of rules, which we know how to deal with, okay? And these are all the rules that we need to go back to our initial case. So what do we do with these rules? Now we finally follow the ordering in the right way. So we start from blue. We start from blue and we say, okay, are there any rules where blue appears in the head? And we look and we say no. Okay, then this tells us that the lower bound should be 0 and the upper bound should be 1. Good. We go green. We look at green and we say, is there any rule where green appears in the head? And we see that there is none. So we can say again, the lower bound is 0 and the upper bound is 1. Then we consider yellow. Now for yellow, we have no rules with negative head. So we have upper bound 1. However, we have two rules with a positive head. So what we need to do? We need to consider both of them, and then we need to take the strictest. So we need to do a maximum, right? Okay. Finally, we take red, and here we have both a rule with positive head, which gives us the minimum between blue and 1 minus green, and a upper bound, which gives us 1 minus the minimum between 1 minus green and 1 minus yellow. Okay? So this is now essentially what's nice is that we know exactly, if we want to satisfy our requirements, what is the lower bound and the upper bound that each of the labels need to satisfy in order to be compliant with it. So what is left to do? Well, this is very easy. For every class A, then we simply compute the final value as the minimum between what? The upper bound and the maximum between the output itself and the lower bound. So imagine, this is nothing else than doing this operation. You have a lower bound, you have an upper bound, and then if your output is greater than the upper bound, you put it equal to the upper bound, and if it's lower than the lower bound, you put it equal to the lower bound. So literally, you're just doing this operation of putting the output back inside the boundaries. And yeah, so basically we're done. And here there is just a general overview of the method. So you take your requirements, you define an ordering. This allows us to transform the requirements into rules. You can forget about saturated rules. This is to get the stronger requirements. Then what do? We build a dependency graph. Why? What is a dependency graph? Well, it's just a way of optimizing things, because if you think about it, when you have a GPU, it's very good to parallelize. So you don't want to have a total order of your labels and do as many steps as the labels that you have. But if you have two labels whose values is completely independent, then they can be computed at the same time. And that's we can parallelize their operations. So the dependency graph is nothing else than a DAG where we plot all the dependencies, and then if two labels are at the same level in the graph, then we put them, we compute them in parallel. And yes, this allows us to do things a bit faster. So yeah, then thanks to this, we can compute these levels, and then we can compile our layer. Okay, so this is the theory. Now the question is, how does this do in practice? Well, as a cool case, we use the RODAR case, which is the dataset Vifek was mentioning, which is a dataset for autonomous driving, where you have a bounding box around each of the relevant agents, and then each of the bounding boxes annotated with the agent that is inside, the set of actions, and the set of locations. And this comes with 243 requirements, annotating propositional logic that tells you things like, in the bounding box, there should always be an agent, a traffic light cannot be red and green at the same time, or, you know, if there is somebody is pushing something and it's a pedestrian, it cannot be a car or a traffic light. So all relationship between the label, yeah, sorry about this. So there are all the code requirements express all the possible combinations around of the labels of the bound that can be associated to a bounding box. And yeah, so if we have a standard model, we have actually tested action detection models. These are the predictions that we can get. And as you can see, this makes no sense, because we can have a traffic light that is red and green at the same time, and we know that this cannot happen. So we have also the requirement that tells us so. And then what we have done is taking exactly the same action detection model, putting our requirements layer on top, and this is the prediction, the same prediction that we get. So, okay, so it's nicer to show this, and it's good, but the question is, okay, you know, this is just a qualitative example. Does it actually help improve the performance? And the answer is yes. So this is the frame mean average precision that we get throughout training. And this is the final framing average precision that we get with this basic, the standard action detection models. All of the others are variations of our method. Why do I say variations? Because if you think about it, obviously we were defining an ordering, and then the layer we define is dependent on the ordering. So obviously the ordering has an impact on the performance. However, the good thing is that even if you pick a random one, which is the pink line, you still get something that is better than not using the layer. However, you can come up with ways or sort of heuristics to define you know, orderings that actually give even better performance, which are the ones on top. And yeah, so this is just to show that even on a complex dataset like RODAR, then injecting the requirements actually improves the performance. Then also to show you how the model performs against the state-of-the-art models, we have tested this on, I think, 16, if I remember correctly, tabular multi-level classification problems with a bunch of requirements. And CAMEL, ECC, BR, RACL are all state-of-the-art models for multi-level classifications whose then prediction has been changed via post-processing. And SPL is a semantic probabilistic layer, which is essentially a layer that, again, tries to enforce the constraints, but with a sort of probabilistic semantics to it. So it does, it's essentially compiling the constraints into a probabilistic circuit, and actually it has a bit different flavor to it from what we do, but it can guarantee the satisfaction of the constraints. And CCN is the older version of this model. And as you can see, CCN Plus actually outperforms each and every one of them. So yeah, I mean, this is good and actually performs very well. Finally, just last point. In our most recent work, actually, what we have noticed is that propositional logic requirements can actually be treated very similarly to linear inequality, requirements expressed as linear inequalities. And so what we were able to do is essentially define again a layer when you have constraints expressed as linear inequalities, following exactly the same procedure. So by defining an ordering, by doing all the possible reductions that are necessary, and then building a layer on the ground of this. And this actually allowed us to apply this to the data generation problem. Why is this important for data generation problem? Well, because as you can imagine, when you are generating data points, you want them to generate data points that actually make sense, that are compliant with your background knowledge. And actually, if you go and talk with people working in industry, this is often not the case. You take, I don't know, variational autoencoder, you take a generative adversarial network. Most of the time, we generate tabular data that make no sense. And so essentially what was done before we developed this model was generating data points, and then whichever didn't make any sense, throwing it away. Okay. However, thanks to our model now, what we can do is again generate data points that are compliant with the requirements and actually also get better performance. So just to give an example of what we can do, we took this data set, which was collected on a clinical, collects data from the first 24 hours in the ICU. And essentially the requirements are a bunch of medical things, but the one that I want to show you is that the maximum hemoglobin recorded in these 24 hours should obviously be greater or equal than the minimum hemoglobin that you recorded, right? And if you plot the data points, you get obviously something that is compliant. However, if you plot the data points that you generate with TableGAN, which is a standard method, a generative adversarial network, then you get something like this, where you can see that actually you have a lot of data points that actually violate the constraints. If, on the other hand, you use our layer, which can be simply inserted, then you get this distribution, which not only is compliant, but just to give you an idea, if you compare it with the one that is of a real data point, is actually even more similar. And yeah, so this is actually good. We can actually do something better, well, which is not only safer, but is also actually better. And before somebody tells me, oh, but again, we can simply throw away the data points that are not compliant, and this doesn't really happen in practice. I just would like to show you this table. These are the number of the percentage of violations that you get when you generate data points with these models. And as you can see, we have multiple cases where you have 99.9 or 0.8 percent of the data points that are not compliant with the requirements, and one case where we even have 100% of the data points that are not compliant. So what do you do in these cases? Like, if you are, for example, using an Amazon AWS instance, then this would be very, very costly, right? And also not very good for the environment, if you think about it. Okay, so just to wrap up, we have actually put all of our work into a package. So if you're interested, you can just install it. You can just do pip installed file shield. And this gives you access to a function, which I think, if I remember correctly, is called compile requirements layer or something like that. And essentially, you can pass to it a TXT file where you have written your requirements, and it returns to you a PyTorch layer, which makes your model work better and make them a bit safer. And yeah, well, this was it, just some open questions. Right now, we are trying to further extend the syntax. We would like to apply the same intuitions to autoregressive problems. And finally, one day we would like to drop the fully supervised assumptions. And yeah, we would like to work in the semi-supervised case, which is a bit more what the standard neurosymbolic problems do. And yeah, thank you very much for having me. Do you have any questions?
Thanks very much, Eleonora. Can you hear me?
Yes, absolutely.
Yeah, so if you stop sharing, you might then
Yes.
also see if people feel free to write on the messages while Eleonora looks at the questions. I had a few questions from my side, Eleonora, to just get started.
Yes.
If I had to summarize, and I mean, it's a really interesting talk. If I had to summarize, let's say I was not a logic person at all, and I looked at your talk, and there was quite a bit of subtlety in terms of variable ordering, in terms of how exactly you map these into constraints. But let's say I just took the time to understand the Gödel T norm. Could I then say, you give me a propositional constraint, I'm going to apply a Gödel T norm translation and use this as a loss function for my deep learning problem, and that's it, that's all I need to know? Or am I missing something?
No, so this is kind of what LTN does, which is
Yeah,
you take a T norm and you apply it in a loss function. What we do is we have a layer.
yeah,
So, and that's one thing. So essentially, instead of having a loss function which sort of directs, your learning, this is a
yeah,
layer that actually changes your outputs. Okay.
right.
And
Yeah,
then secondly, you cannot, because we want this guarantee, you cannot just apply the Gödel T norm, because if you think about the simple constraint, A implies B, and B implies C, right?
yeah,
Then you cannot, if you just use the Gödel T norm, you get for B maximum between A and B, and for C the maximum between C and B. However, you have no idea of the relations between A and C. So what our compilation does is literally trying to do also in an optimal way to get all the entailed requirements that give you all the constraints you need to get something that is coherent, because you don't want to miss these things. Also, you need to pay attention, because if you don't want to, derive all the possible entailed requirements, you need to be smart about it, otherwise the problem really explode. And so our procedure also allows you to do this in a very efficient way, in a minimal way. And actually our complexity is more defined by how the constraint, by the graph of the constraints rather than the propositional logic. Sorry, by the
Yeah.
number of the variables.
So I guess that brings
Sorry.
me, you talked a little about hierarchical constraints. So what's the biggest constraint you have used in some of your work? I mean, how many variables, propositional variables are we talking about? Like you mentioned, 243 requirements for the RODAR data set. Are you expecting the network now to satisfy all of them or only one of them? All of them.
All of them at the same time.
How many variables are they altogether?
So on the RODAR, it's a very simple case. It's only 243 requirements, 41 labels.
Yeah.
But for example, in the hierarchical case, because we were working with protein function prediction, we had 4,000 variables in the worst case.
Okay.
I don't remember the number of constraints, but I can tell you the hierarchy was 13 levels deep.
Yeah. Yeah.
So
Okay,
it
nice.
was
Yeah.
quite a bit. For example, we tried this also on the data generation case. We tried to compile linear inequalities with, I think, something like 300 variables. And the longest constraint had the 90 variables appearing. So that
Nice.
allows you to see, how fast you're actually going, right? That's why
Yeah.
it's important to have
Yeah.
this dependency graph and everything to do the parallelization
Yeah.
well.
Yeah. Very nice. Eleonora, there are a few questions in the chat. I think the order is Lauren, Michael, Matt, and Alex and Arthur. Maybe, I mean, if the people want to speak up, of course they can. But before you answer them, if you could just tell the question to the audience in case the YouTube video wouldn't,
Yes.
have access to the chat.
Yes, right. So Lauren is asking that, essentially, just to summarize, that generative models are already quite expensive to train. So maybe an idea would be, instead of adding the constraints from the beginning, one could add them as fine-tuning. So actually, we haven't tried as fine-tuning. I think it would be actually a good idea. We have tried either to add them as from the beginning during the training, or you can also use this layer as a post-processing step, at least an efficient one. And so what we have seen is that obviously now you get the guarantee that the constraints are satisfied, but then it doesn't really improve the performance, right? Because you're just doing some post-processing. So I guess if you do this as fine-tuning, you could get something in between. Maybe you don't get as big improvement in performance as if you're training from scratch, but for sure you can do a bit better than post-processing. So actually, it's something nice to try. Then we have Lauren, I hope I answered your question. So then we have Matt that asks, what is the scope of the properties rules that you can include currently in these constraints? Could only propositional logic, or could you also include constraints like y major than 3x plus 5? So as of now, if you download PyShield, you can get either propositional logic, so A or B, blah, 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 or you can get linear inequalities. We are literally working right now to ship the version where you can have disjunctions over linear inequalities. So hopefully soon, but if you are just interested in linear inequalities, like conjunctions of them, it's there. Then we have Michael that says, you argue that neural network verification is performed too late into the engineering process. Model for RODAR was found to not satisfy requirements, and you add the requirements layer to make the model satisfy requirements. Is adding layers still not too late in the process? Can these techniques be combined, or are they separate? So actually, this is a very good question, and because actually, when you give a talk, it's difficult to pass all what you want to say. I said obviously that something that was bugging me was the fact that these things are too late into the process, but that was to mean that this was all that was out there when I started this process. And so I wanted to have something that was acting a bit earlier. However, I don't believe that what I do is a silver bullet for everything, because again, I'm an engineer, so I believe you need all of this to make neural network safe. So you need layer, you need to, whatever you can encode by design, but then there will be obviously some properties that we won't be able to encode. And so you need verification, you need testing, and everything hopefully will help to make this neural network safe. And adding the layer is still, I don't think it's too late into the process, in the sense that it still belongs into the model design bit. So it's still into the second step. And is actually trying to combine these requirements into the creation step. So they are not separate. We were literally, the goal was literally trying to merge them. And yeah, I think honestly, in practice, we will need to combine everything to make things safe. And actually, to be honest, we are even trying to use the requirements a bit earlier into the data annotation phase. So, you can be smart about these things, and you can use requirements to actually check your data set a priori, or we used it in the annotation phase itself to make the annotation more efficient. Like you can simply use your formulas to check whether an annotation satisfies them or not, and we use the Maxa solver to propose possible corrections and make the annotators work faster. So absolutely, that was sort of a bad thing that I said at the beginning of my talk, but I think we need everything to make this model safe. Cannot be just inclusion of a layer, verification of testing. We need everything. Again, hope I answer your answer, sorry. Then we have Alex.
Thank you.
Oh, good. No, okay, perfect. Then we have Alex. Do you see a ceiling to the complexity of the requirements, e.g. for a mortgage application? I'm not sure I understand. So, sorry, the question is, do I see a ceiling for the complexity of the requirements? And then it says, for example, for a mortgage application. I'm not sure what you mean by for a mortgage application. As of now, we haven't hit the ceiling of the complexity. Obviously, every time is a big headache to extend the syntax. Like I can tell you, going from hierarchical to rules, from rules to propositional, linear inequalities, every time it's a big headache. It's not easy, but for me, it's a very interesting open problem. So for now, we are happy to keep extending it. I don't know what you mean for a mortgage application. So I
If
don't
I
know
had
if
to
you can.
guess, Eleonora, I was thinking maybe what Alex might have meant is kind of what I was hinting at in my question, in the sense that if you were going to build a deep learning network to predict, let's say, successful loan applications, and you might have many constraints that go into whether somebody should be granted a mortgage or not, for instance, where they stay, what kind of history they have, et cetera, et cetera. So then I think it starts becoming like relational constraints. Maybe there's some organizational or structural complexity you want to introduce before you grant somebody a mortgage. And maybe what they mean is it could be, fairly complex first order constraints that come into the picture if you're thinking about that, whether you potentially, unless, Alice wants to speak up, but yeah, that's what I was thinking.
Yeah, actually, these are two different questions because the answer and it was like the requirements in the real world, like a bank loan, can be very non-mathematical. So
Yeah.
this is fun because actually the data generation problem started from a bank that actually had the problem of generating data points to check their systems to reject overdraft applications, and they have obviously a bunch of rules. I don't know if a human is involved that can be non-mathematical, but they have a huge amount of rules that are very, very mathematical and they are clearly encoded into formulas. So obviously this method has the limitation that you need to have requirements that are precise, that are formally expressed, and they need to be formally expressed. It's not something that is designed to take, natural language process, like a natural language requirement and encode that. So that's obviously a limitation. But, as I said, to make neural networks safe, we need everything. And this is very much in the realm of if you have a set of formal requirements, but you need to be satisfied because you might also have requirements, not when you're not talking about requirements, but you have constraints that, are so satisfied 90% of the time, but not always, then this is not the right method for you. Like you need something like LTN where you're incorporating things into the loss. For us is, suppose you have something that you know for sure you want to have satisfied, this is like what we propose. So that's it. And yeah, regarding the complexity of the requirement, obviously they can be very complex. We are trying to extend the syntax. Up till now, we have propositional logic or linear inequalities. We hope to extend it very, 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 very soon, like literally now. So we are already doing that. So yeah. Then we have Arthur. Can you tell us a little more about how the layer is built? Is it a sparse network? In your slide, you had the fact that three layers for green, blue, and yellow, and then red. Thanks. So how it's built is very, very simple. So if you have all the entire procedure, then it's nothing else than a series of maximum, minimum, and one minus. And if you implement things with PyTorch, all of these operations have been optimized like crazy. And if you actually, what we try to do is obviously to try to make them happen, all of them at the same time in parallel. So imagine if you have A and B, A implies B, and C implies D, then you would have two maximums that happen at the same time. So it's essentially a maximum over a matrix. And well, as of now, we had no problems in terms of memory because exactly we have this division in layer. So we have all operations over very dense matrices. If we ever hit the ceiling of, them becoming too big, we will look into how to have also a sparse version of it. But so far, we have been very happy with dense matrices, and everything is implemented in PyTorch.
Lovely. I think
yes.
those are the questions, Eleonora.
Yes.
Fantastic. Thanks everybody for joining us, and thanks Eleonora for taking the time. I think this is really helpful going into the detail, and I think I really liked your examples. This should make great teaching material for your classes. So that's
Yeah,
great.
I hope so.
Yeah, thanks again, Eleonora, and see you at
Yeah.
some point in the future. Bye,
Oh,
everybody.
for sure. Bye. Bye bye. Thank you for having me.